of my parameter theta following the direction of the gradient, right? And I'm going to refer to this case as stochastic gradient descent with IID data, because at each iteration, the Z, the data I can draw, is independent, and they are going to be drawn from the same distribution mu. Now, I use this algorithm a lot in my own application context, which is I'm from the field of operations research. So in a lot of online learning problems in operations research, we use this type of algorithms to learn like what's the optimal policy or what's the optimal parameters to use, right? But I also came to realize that in the setting that I'm interested in, a lot of the times the feedback not only is a function of my current decision, but it's also affected by my prior decisions. So at a very high level, I'm going to demonstrate this through like a simple single server queue example. Okay, so here my goal is to learn what's the right price to charge for my single server queue. Okay, the price is going to affect the demand, which is in the form of some arrival rate function. So I'm going to assume that the arrival rate function for this single server queue is going to be a function of the price that I'm going to charge. Okay, let's say I start with a very high price, $5 per person. Okay. It's going to take me a while to see how the queue evolves over time to probably realize $5 is too high a price to charge, because I see that my queue are constantly very low and my servers are idling most of the time, right? So I realized, okay, this is too high a price in an online learning fashion. Okay, let's adjust the price down to $2. What will happen here is that I will not immediately see the queue grow into a very large number, even if $2 is too low a price, because I start with that low queue induced by $5, right? So if this is a system that is keep running, I start with a very low queue because I was charging too high a price before. So it's going to take me a while to realize that maybe $2 is too low a price to charge, because it's going to take a while for the queue to grow eventually to the corrected queue length that would correspond to $2. Right? And then I realized $2 is too low a price to charge because the queue is too high. So I adjust the price up again, maybe to $4. Now, $4 might be the right price to charge. So I see a reasonable queue. But the problem is that I start with $2 in the previous period. So there's a huge backlog of customers in my queue, right? So if I just look at how the queue looks like, it's again going to take me a while to realize that $4 is the right price to charge. It actually gives me the right queue length that I want. So in some sense, for people familiar with control theory, I'm running into some problem of delayed feedback, right? So my current state is not only influenced by the current price I'm charging, but also the price that I charged in the previous period. So if we are running things in a fully online fashion, like the stochastic gradient descent here, we might have extra oscillation due to this delayed feedback. So this is the problem that I'm interested in looking at here. More precisely, I'm going to define my loss function as follows. So the only difference between the loss function I define here and the standard setting is that the parameter theta not only enter my loss function capital L, but it also affects the distribution that is generating my underlying data. Okay, let's think about theta as the price that I'm charging. Right? It not only affects my revenue, but it also affects the queue length process, the dynamics of the underlying queue length process for that single server queue. Okay. Now, in particular, in this case, I'm going to assume that the underlying data is generated according to a Markov chain whose transition probability is indexed or is parametrized by this parameter theta. In this case, mu theta actually corresponds to the stationary distribution of this Markov chain. Now, the problem of running the same stochastic gradient descent algorithm in this fully adaptive online fashion is that at each iteration, I essentially just run one step of this Markov chain under my updated parameter theta t. Right? So in this case, the distribution of zt could be very far from the stationary distribution that I'm interested in. So in this case, if I evaluated the expected value of this gradient estimator, it can be far from what I'm really interested in, which is the gradient estimator evaluated under the corresponding stationary distribution. Now, just to give some concrete example to see where this type of problem is going to arise, let me go back to this queuing example, which is kind of a popular example in the OR literature. Okay, so here I'm trying to learn what would be the right price to charge for my single server queue. I also have some control over how fast I should serve customers. So I also have some control over the service rate here. And if I look at the waiting time process, so this is the waiting time of the T's arrival to my system, then it actually follows this very nice recursive formula. So it's a Markov chain, right? So this is known as the linked list recursion. It says that the waiting time of the +1's customer is equal to the waiting time of the T's customer. So I have to wait at least for the T's customer to end her service. And this is how much it takes me to serve the T's customer. And then I subtract the time between the T's arrival and T+1's arrival. Okay. And I think the positive part of this is basically the waiting time of T+1's customer. So here, what I'm interested in is, well, now I'm maximizing some function, which have a revenue here. So the price I'm charging times the demand arrival rate. I pay a cost for providing faster service. So there is some cost associated with how fast I serve customers here. I also pay a cost by keeping my customers waiting. So this last term here is basically a penalty for like bad quality of service or keeping customers waiting. Now the thing here is that the parameter that I'm trying to optimize not only enters through these terms, but it also affects the dynamics of this underlying waiting process. Okay, and what I'm interested in is some like long-run average cost minimization problem. So I'm interested in the stationary waiting time under the price and mu, the price I charge and the service rate I'm using. Now, similar to what I described before, if I do this update of this parameter in a fully online fashion, meaning that I see an arrival and then I do a gradient update of this theta t function, then what is going to happen is that I still have a Markov chain, right? It still follows this nice recursive formula. But because these mu t's and pt's are keep changing from one step to another, so now I'm actually dealing with a non-stationary Markov.
What is stochastics, PT and mu t? They independent of everything else, or PT, MT? What are they? These are random, yeah.
PT and mu t.
Yeah.
These are my decisions. So I decide.
Are they random? How do you choose them? Is basic on the basic of previous observations or not?
Yeah, so I could learn them in an online fashion, for example, following some gradient descent step.
So some in Markovian setting, yeah, Markov chain, yeah.
Yeah, I could follow a Markov chain.
MT, so it's okay. So it's, you have something like Markov controlled, Markov adaptive, Markov chain. So you have Markov chain for PT mu t, and based on that you do.
So PT mu t is the rule I set. I could follow some Markov decision rule to decide what PT mu t is. I could also throw in arbitrary PT and mu t. Yeah. So like right now, I haven't talked about how I determine what PT mu t to set. Yeah. But this is like my decision variable. Think about me as a manager. I can decide what price to charge and what service rate to use.
So based on PT mu t, you run this Markov chain, yeah. So if PT mu t are given to you, then W makes a Markov chain.
Yes, exactly. Yeah. But yeah, so I'm assuming like given PT mu t, WT is a Markov chain, but PT mu t is changing over T. So this is a non-stationary.
Yes, of course. Markov is a mu t, PT mu t may make its own Markov chain. And then you run another Markov chain, which is operated by another Markov chain.
Yeah, it could be the
Markov modulated Markov chain.
Yes, it could be.
That's what it is.
Yeah. Okay, so now there is another question here, right? If I want to do like, how do I determine PT mu t? I might want to follow some gradient descent or gradient ascent type of updates. And in this case, how do I actually estimate the gradient of this expectation here? So I will come back to this problem a little bit later to see how we address these two problems here. Okay. My second example is of very similar flavor. So this is about a news vendor problem, essentially like thinking about you running a small store and deciding like how much inventory to order in each period. Okay. The only caveat I'm adding to this problem is that the demand, I'm going to assume it's not IID for each period. Instead, it actually follows a Markovian autoregressive process. And if you ever have a stock out, meaning that a customer walks into my store and cannot find the products that he or she wants, then it hurts the reputation of my store, which gonna carry over to the next period. So maybe there are gonna be less customer coming to my store in the next period, okay? So this is what we call a dampening effect. So essentially, whenever I have a stock out, there are gonna be some customers that are not happy, and these gonna influence my demand in future periods, okay? Now, in this case, my loss function is a standard news vendor type of loss function. I pay a penalty for having more inventory than the demand. So there's an overage cost. I wasted this inventory if I cannot sell them for. And there's also an underage cost. So if my demand is greater than the inventory I order, then I have make some customer unhappy. So there is also an underage cost. So theta is my decision here, which is how much inventory I'm going to order in each period. Okay. Now, if I try to learn what's the right inventory level to order in a fully adaptive fashion, then that basically means that my theta t is going to change from one period to another. And again, this gonna give me a non-stationary Markov chain because of these varying theta t values, right? And due to the transient behavior here, the expected value of dt is going to be far from the corresponding stationary distribution. So I run into the same problem as what I had before. Now, the last motivating example is a policy gradient in reinforcement learning. Okay, so here I'm going to consider the setting where my goal is to minimize the cumulative discounted cost over time. So gamma is the discount factor. Okay, C is the cost I incur in each period. The C is going to depend on where I am, so my current state, ST, and what action I'm taking in each period, so AT here. Okay. Now, this discounted cumulative cost can also be written as some expected cost with respect to what is known as the occupancy measure in the RL language, okay? But what this occupancy measure is in this case is also a stationary distribution of a Markov chain. And the stationary distribution has the following transition dynamics, okay? So gamma, the discount factor, is actually serving the role of regenerate this Markov chain. In particular, in each period, with probability gamma, I'm going to redraw the state of the Markov chain according to some initial distribution role, okay? And then with probability 1 minus gamma, I'm going to follow the usual transition kernel of the Markov chain to move to the next period. So if I run this type of Markov chain, then this so-called occupancy measure is the stationary distribution of this discounted chain.
So gamma is chosen for the whole period, regeneration period, single gamma for each generation period, yeah, correct?
Yes. Yeah.
And
So
then,
that summation should have gamma raised to t.
This is for each.
No, the one line before.
This.
That sum should be discounted.
Oh, yeah, you're right. So I should have.
Sorry,
it.
interrupted.
Thank you. Yeah. Yeah. And here, sorry, what is theta? I'm assuming like my policy of this MDP can be parameterized by theta. Okay, theta is some parameter that parameterizes what policy I'm using to generate these ATs. Okay. Now, in terms of how to estimate the gradient of this loss function, someone has already done the hard work. So it turns out that there's this very nice formula characterizing what should be the gradient of this loss function here. Okay. Basically still an average with respect to the occupancy measure. Okay. And it has this Q function here, which is known as the state action value function. Okay. And it also has the gradient of the log of the policy function. Now, the challenge here is basically how do we sample data from this occupancy measure? And also how do you come up with a good estimator of the state action value function? So this is almost the same challenge as how do you estimate the value function here. Okay. So I'm going to come back to all these questions later, but this is kind of the classic problem that motivated me to study stochastic gradient descent in an adaptive environment. Now, this is the problem we start with. Okay. If I'm going to say that it's actually not going to be a very hard problem because I can still do something pretty similar to the IID set. How do I do this? Well, I can do this by fix the policy, run the Markov chain for a long enough time such that it gets close enough to stationarity, right? So if I fix the policy at iteration k, at theta k, I'm going to run the Markov chain. Now this is a time homogeneous Markov chain, right? And hopefully by having a large enough batch size, the Markov chain towards the end of this period is going to be close enough to stationarity. And I'm going to use this to construct some gradient estimator, okay? And then I'm going to go back, update my theta again, and run this batch type of updates, right? If I carefully design what's the batch size here, I will get close enough to stationarity. And these updates I use, these samples are approximately independent of each other, right? So then I'm really going back to the IID set. So this is actually the idea that has been used a lot in the literature, in both the online learning example I described in OR, also in the reinforcement learning literature. Okay. But in this work, I'm going to push things a little bit to the extreme. I'm going to ask how adaptive I could be in this environment. Is it okay that instead of doing this like carefully designed batch updates, I'm just going to run the Markov chain for one step? Is it okay that I just update the Markov chain under the new policy for one iteration? And then I'm going to use this to directly go to update my underlying parameter. Okay. Would I still have good convergence property if I do this fully adaptive update? Well, a preview of the main result is yes, under certain ergodicity and continuity conditions that I will introduce next. Okay, so essentially the main contribution of our work is to characterize these conditions under which even if you do gradient descent in this fully adaptive manner here, you still have very similar convergence rate as the IID case. And we will show that these conditions actually are pretty applicable to all the problems or examples that I just used. Now, before I go to our main results, let me just talk briefly about the related literature to put our work in the right context, okay? SGD with IID data has been well understood, well studied in the literature. And again, I'm talking about the light tail case, okay? Now, there has also been some work for SGD with so-called dependent. But the key difference there is that these dependent data are generated from a Markov chain whose transition dynamic is not influenced by my data. Okay. Even though the DTs are dependent with each other, but they are generated from some exogenous fixed Markov chain. Okay. The setting I'm considering, where the transition kernel of the Markov chain is also affected by my parameter theta, is known as SGD with adaptive data. And this has been studied in some previous work. The main difference between what we are getting here and these work are that our assumptions are different. And as I will explain later, I feel like our assumptions are more general, easy to check, and applicable to the type of applications that I'm interested in. So the work that I'm talking about is also related to online learning in operations research and also sample complexity for policy gradient algorithms. So the main difference between our work and these applications is that they use some similar idea as what I said before. So they do this carefully designed batch updates. Hopefully by running a long enough batch, they get around this issue of adaptivity. And lastly, I'm going to actually use some results from the simulation literature called infinitesimal perturbation analysis, which is essentially taking a sample pathwise derivative. Okay, and this is the way that I'm actually going to come up with good gradient estimators, some of the examples that I'm going to talk about. Now, let me first talk about our main result. So under what conditions we can still do update in a fully adaptive manner while still converge, have good convergence properties. Okay. The first group of assumptions I require here is essentially the underlying Markov chain converges to stationarity fast enough. So there's good ergodicity properties of the underlying Markov chain. Essentially, what I require is that there exists a common Lyapunov-function V, okay, which is satisfied for all the theta in this constraint set capital theta that I'm interested in. Okay. In addition, I also require a Wasserstein contraction property. Okay. So essentially this chain converges to stationarity exponentially fast is what I'm requiring here. Under these conditions, we can characterize the so-called mixing time of the Markov chain.
What is X? What is X?
It's the starting point of the Markov chain.
No, X, what is a Markov chain? You have two component Markov chain. It's
Okay.
Markov chain itself, Z.
Yeah, it's a Z under the transition for a fixed theta.
Fixed theta.
Yeah.
This condition is for a fixed theta.
Yeah, these conditions are for any fixed theta. And
Okay.
Yeah.
And rho is the same for all theta.
Yeah, exactly. So I have the same.
Less than one, yeah.
I have the same Lyapunov-function and the same rho for all thetas. Is what I chart here.
Okay.
So here, of course, sometimes the first condition, the existence of the Lyapunov-function, would automatically imply the Wasserstein contraction, right? For example, if I use this particular distance, the ring is constructed based on the Lyapunov-function I'm using. But as we'll talk about later, having a little bit of flexibility to choose what distance we use here will allow us to handle like larger possible problems. So I'm still listing these two as two separate conditions here. Okay. So this is the first group of conditions I require. I require the underlying Markov chain to mix fast enough. Okay. The second set of conditions I require, okay, at a high level, what I want is that from one iteration to another, I'm perturbing the transition kernel of the Markov chain a little bit, right? It's a Markov chain with transition kernel p theta t. I'm perturbing it to a Markov chain with transition kernel p t theta t plus 1. Okay, I want some continuity of this perturbation. Essentially, I want to say that if theta moves a little bit, then the transition kernel wouldn't move by too far. So this last piece is really the most important one I require here. So this is the one-step transition kernel. So if I perturb from theta to theta prime, then I require some Lipschitz continuity of the underlying transition kernel here. Okay. I of course also require some continuity, Lipschitz continuity of the gradient of the function, and this stochastic gradient estimate. These two assumptions are what differentiate our work from the previous work. First, for this one, previous work actually required the G function to be Lipschitz in Z with respect to the Euclidean distance, rather than this more flexible distance I'm using here. Okay. For this, for example, if you have a gradient estimator that takes the form of an indicator function, then this assumption, the old assumption wouldn't hold. Okay. But here I do have the flexibility of like using the total variation distance type of distance, and this is like essentially any function. This one, basically the literature requires to check the solution of the Poisson equation is Lipschitz continuous with respect to theta. Okay. But if I solve the Poisson equation, I essentially solve the NDP, right? So there's a little bit like very hard to check that type of condition. While here, we only require you to check the one-step transition kernel. And the reason that we're able to relax this assumption from the previous work is because we're leveraging like the Markov chain perturbation theory here. Lastly, we require some bumpiness assumption. So we require the gradient of the loss function to be bounded, and we require the stochastic gradient to be bounded by the Lyapunov function. This is again a relaxation of blendedness in the literature. We do not require the stochastic gradient to be bounded. We just require it to be bounded by the corresponding Lyapunov function. Now, under these assumptions, we can prove the following stuff. First, let me talk about the non-convex case. So no convexity is assumed here, but we do assume smoothness as I laid out in the previous slide. So in this case, unfortunately, we cannot do projection. Okay, when we do not have convexity, projection will mess up things. So here I can only do the stochastic gradient descent without projection. Okay, in this case, we can show that if you do this stochastic gradient descent, you're gonna converge to a stationary. I don't have convexity, so I only converge to a stationary point at speed 1 over square root of t. So this is essentially the same convergence speed as the IID case. Now, if I'm willing to assume convexity, now I can allow projection. Okay. In this case, if L is convex and I use like a 1 over square root 2 t type of step size, then what I can achieve is that I can converge to the minimum. So this is an average version of the parameter estimate, right? So this is a weighted average. The average of theta t is going to converge to the optimal at rate 1 over square root of capital T. Okay. If I have strong convexity, I can use a step size of 1 over t, and then I can actually achieve a 1 over t convergence. Okay. These convergence rates are actually pretty much the same as the IID case. So this is basically saying that even though I'm running SGD in an adaptive manner with adaptive data, but I essentially achieve the same convergence rate as the IID. Okay. And note that here I also have the dependence on the mixing time. The tau does the mixing time of the underlying Markov chain does affect my work.
So what happens in between for different powers of T? I mean, you have these Robert-Polyak averages, and they need to go to 0, but not fast, not quick. So is there some in between regime, or do you have some guess of, or maybe the error?
Like instead of 1 over square root t and 1 over t, I have something.
Yeah, maybe a T to thirds or.
Yeah, so I don't have a good understanding of the in-between rate. It's kind of like I carefully tune this rate to achieve the best convergence I can achieve here. I
For
carefully
the
tune this
loss
step
and
size.
then. Right, sorry.
So it's not as general as the what the Polyak-Hilbert averaging is able to say.
Yeah, no, sure. No, that's
Yes.
So I have a stupid question. So you get this 1 by square root of t rate, right? If we just go into the very basic setting of online gradient descent, so the regret bound is also like square root of t,
Yeah, exactly.
more or less. But there, if we go just the regret bound thing, so there we don't assume that x is coming from an IID setting or anything. So we don't. So it's like an adversarial setting, right?
I see.
So
No, you assume the underlying data is sampled from the underlying like data set, which is like IID samples from the empirical distribution of your data set.
So in online gradient descent, in adversarial case, there are these GT coming to the regret bound. There we also don't assume IID, if I'm not wrong. So
Yeah, but there you do not assume the underlying data distribution is affected by theta, right? So theta is affecting the loss function, but the data is not coming from the data, the underlying data generating mechanism is not affected by data.
makes sense. I see. And why? So where does this log come from? Like log t to the power?
Yeah, so I don't think these bounds are tied. These are upper bound. So these log t's are basically coming from technical derivations. So I don't know like what would be my guess is a lot of the log terms can be reduced or even removed. But I don't know how much we can push that.
And this tau is basically mixing time, right?
Yeah.
So
Also, like, I guess I would assume the mixing time would enter through the linear term here, but somehow we have a quadratic term here. So this is also some limitation that I think can be improved.
right. So in your previous slides, you assume that fast mixing is happening, like exponentially fast mixing, something like this, right?
Yeah, exactly.
So if there is no fast mixing, then still you can get to these results, or
No, I need to assume this type of like exponentially fast mix here.
thank you.
Yeah, so there are a lot of I guess additional things that can be developed here.
And you don't have lower bound for.
So this is our main results. Now I'm going to go back to the examples I introduced at the beginning to demonstrate how to apply these ideas. The queuing example is pretty similar to the inventory example, and the inventory example is kind of easier to explain. So I would just talk about the inventory example, but in our paper, we could have the proof of queuing example as well. Okay. So this is the inventory example. Recall that the demand is a Markov chain, and the distribution or the dynamics of this Markov chain is affected by my inventory decision. Okay, and what I'm interested in is to minimize the overage cost when I order more than the demand, and the underage cost when I have less inventory than the demand. Now, one of the challenge I said before is that when I'm taking the gradient of this function here, the gradient is not only affected by these like classic Mies-Bender term, but I also have to think about what's the gradient with respect to this d, right? The demand function also depends on theta. So what I'm going to do is I'm actually going to introduce a gradient process, which I'm going to call LT. This is essentially doing like a pathwise gradient of this demand function. In this case, by just plugging this demand function dynamics, I can have the following gradient formula for this LT. Now, this LT process, I just basically take the gradient of this TP with respect to theta, right? I don't know if it's well defined. I don't even know if it has good convergence property, but at least it can be updated in this recursive manner. So what I'm going to do next is I'm going to consider an enlarged Markov chain field. My Markov chain not only includes the demand process, but also this gradient. Now I enlarge it to both the original Markov demand process, but also this gradient. So it turns out I can actually show that this gradient process has a well-defined stationary distribution. And if I evaluate the gradient process according to the stationary distribution, it's actually an unbiased estimator of the gradient of the demand. Okay. So what we're going to do is now we're going to consider this enlarged Markov chain. And using this enlarged Markov chain, we have this gradient estimator. Okay. If you look at the gradient estimator here, the first term in this bracket here is a classic Mies-Bender gradient. This is like if you take the derivative with respect to the inventory level of a Mies-Bender problem, you have a Mies-Bender gradient. But I have this additional term 1 minus LT here. And this 1 minus LT is basically capturing how my inventory decision is going to affect the demand distribution itself. Okay. So this is a classic Mies-Bender gradient plus an extra term that is capturing the fact that my decision is also affecting the underlying demand distribution. Okay. So what we can show is that this enlarged Markov chain actually satisfies all the assumptions that I require in the previous theorem that I just presented. Right. So after we check this, which is quite easy to check in this case, we can basically say that our convergence analysis, so the previous convergence results directly apply to this. Okay. And notice here, I do have indicator function here. So if I don't have that relaxed Lipschitz continuity condition, then this old theorem that has been developed in the literature wouldn't be applied to this case. These are just some numerical examples to show that we did achieve the desired convergence rate. So I would just skip this because I do want to spend some time talk about the policy gradient in RL example. Okay. So this is the policy gradient example. Recall that the policy phi is indexed by theta, right? And this is the loss function. And here we can actually have a gradient formula for the gradient of the loss function, which can be expressed as this. Now, mu theta, which is known as the occupancy measure, is also the stationary distribution of this Markov chain. Okay. Now, the question we had before is how do we sample from this stationary distribution? And also how do we come up with good Q function estimate? So how do we estimate? So this is a Q function under policy pi theta. Okay, so this is like a policy evaluation problem. How do I evaluate a function, the value function under a fixed policy pi theta? Okay. So what I'm going to do is I'm going to just consider the classic TD type of sampler, so temporal difference learning sampler. Okay. So for a fixed policy, I'm going to sample the state pair STAT, okay, given the current STAT. So I'm going to do something slightly more, smart here in the sense that I'm going to sample another action, okay, which are uniformly at random from the action space. So this helps me do the exploration of it. So I don't need to be restricted by the policy's exploration power. Okay. However, after I sample this A prime T, I'm going to update the states according to the policy pi theta. Okay, so this is like the next state, next action, and next state, next action. So I'm going to sample 2 copies of them here. Okay. I'm only going to use the red copy to update my Q function. Okay. This basically says I'm going to use this TD update to only update one state action pair, which is the ST and the AT function. Okay. And all the other QSA function is going to stay the same as in the previous iteration. Now, if I look at the blue copies here, which are the state action, I'm going to update it to a new state action according to the condition penalty data. Okay. Then I have STAT here, but I'm also going to include this QT into my state space. Okay, now I have an enlarged Markov chain called the ZT. ZT include the current state, the current action, plus a whole matrix, which is this Q function that are evaluated for all SA. So what I'm able to show is that this enlarged Markov chain now, okay, it actually also has some nice convergence. In particular, if my P theta has a finite mixing time, then this enlarged Markov chain, okay, induced by the TD sampler I introduced on the previous slides, also has a finite mixing time under this particular distance. Okay. More interestingly, this the invariance distribution of this enlarged Markov chain has the following nice properties. First, if I evaluate the marginal stationary distribution of ST and AT, it is exactly the occupancy measure that I'm interested in. Okay. And if I evaluate the marginal distribution of this Q function according to the, this V theta, then it's actually equal to the Q function I want under the policy pi theta. So what this says is that if I do this TD learning with constant step size, okay, constant learning, I will not converge to this, but the stationary distribution, the expectation, will converge to the Q function that I'm interested in. Okay. Now, based on this, I can come up with this type of gradient estimator. And then if I do this, then I have essentially an actor-critic policy gradient algorithm. Okay. So this is the step. I run the Markov chain for one step to update the Q function, and then I immediately plug in this Q function to update my state. Now, in this case, we can also verify that the conditions that we require in the previous theorem holds under these assumptions for the MDP problem. Okay. So here, I guess just to demonstrate the policy applies, I'm considering a relatively simple setting with finite state space, finite action space, a non-trivial discount factor, and I require the initial distribution to cover all the states. And essentially, when you do a regeneration, you have an opportunity to move to visit every single state. And I require the instantaneous cost function to be bounded, and I require the policy function to have certain Lipschitz continuity here. Okay. Under these conditions, we can show that the conditions that are required in my previous convergence results hold. In this case, for policy gradient, it's in general, the L function is not convex. So that's why we have to use the non-convex version of our theorem to show that we can achieve like 1/square root of the convergence. And this convergence rate implies a sample complexity of epsilon to the power -2, which is the best known results in the sample complexity for a gradient. I mean, there's similar results of that order established in the literature, but basically our sample complexity result matches the best known results. All right. These are just some numerical experiments demonstrating the performance. So here, I just randomly generate instances of this underlying MDP. Okay, this is a relatively small instance, 5 states, 5 action, and a relatively large, but still very small instances with 10 state and 10 action. Okay, for this, each of these, I generate 100 different MDPs, and here I'm showing like the average performance average across this 100 instances under each of these settings. Okay, so here the different curves are actually using different batch size. So the blue curve is using a batch size equal to 1, which basically means after I update the policy, I only draw one sample and then I update the policy again. Okay. I also tried like a batch size of 10, or a batch size of 100, meaning that every time I update the policy, I actually run the policy for 10 steps before I use the data to update the policy again. Okay. Well, there are some differences between these lines, but they all achieve the same convergence rate. So the black curve is marking the theoretical 1 over square root of G convergence rate. So these are plotted in the log scale. So you see that it does match. Okay, there are slight differences between these lines, but I would argue like this non-rate difference is a constant factor. So this is basically saying that if you just do a batch of size 1 in these settings, you achieve pretty much the same convergence guarantee, right? Which is very nice. At least like you don't need to worry so much about how careful you need to be in designing the batch updates in these settings. All right, just to quickly sum up. So in this work, we studied this particular loss function where the parameter theta not only enter the loss function here, but also affect the underlying data generating mechanism. Okay. And we try to understand when would this type of fully adaptive gradient update still achieve good convergence rate. So what we were able to show is that under suitable ergodicity and continuity conditions, we can achieve pretty much the same convergence rate as the IID. Something that I didn't have time to go much into, but you should be able to see a little bit of that from this inventory example, is that modeling approach is not always conflict with the learning approach, because these days we heard a lot about, okay, this is like a model-free learning algorithm, right? You don't really need a model there. But it turns out if you know what's the underlying model that is governing your transition, then you can construct a much better gradient estimator. Right? Using the sample pass gradient idea, you can actually come up with more informative or more sample efficient gradient estimator to do the estimation. So we are actually exploring this idea further. In particular, my student Ethan, his job market paper is on differentiable discrete event simulation for queuing network control, where he's essentially utilizing this sample pass gradient idea that can actually be used to optimize a large class of queuing network control properties. So hopefully you will have the opportunity to hear him talking about this when he's on the market next year. A draft of this paper is available on my website. We're still polishing, so after we are happy with the final draft, we'll also post it on archive. Thank you very much.
Thank you. Maybe we can take some question while the next speaker sets up.
Just wanted to ask, like, again, a very stupid question, but if you go to this Markov chain perturbation theory slide,
Yes.
yeah, so basically the conditions are similar, like in this, like something similar in this paper, right? This
Yeah,
paper.
exactly.
So the ergodicity also, so they have like 3 conditions and they show some bound between Wasserstein.
So what they were shown, they also require the ergodicity assumption I had on the previous slide. And they show that if the one-step transition kernel
Yes.
is not perturbed much, then the corresponding stationary distribution also doesn't change. And the convergent speech similarity also doesn't change.
Right. So question is like, so what I was trying with this, like in almost all the cases, when I was trying to see that, like if some gradient descent satisfy like this condition, I always manage to like stuck into that. I somehow have this gradient dominance condition, and there you can get like 1/t rate. So some kind of PL inequality or something. So I don't know, like if you have a non-convex function and still these conditions are like, can be satisfied, like some general non-convex function.
If I have a general non-convex loss function,
Yeah. So if you have SGD iterate for this general non-convex loss function, I was not aware that like these 3 conditions can be satisfied.
so I guess the loss function is a little bit different from the P data because this is how the underlying data was generated, right? The only thing I would worry about when I do not have convexity is that I require these conditions to hold for like basically the whole space. I cannot do the projection. So I think the real difficulty in the case where you do not have convexity is that you will not do the constraint sets. You have to make sure these conditions satisfy on the whole space, like basically RD here.
Right.
Right. So that I think it's true that in some applications, you do
Yeah.
require this to be.
Yeah,
some
exactly. So you have to be like compact sets. So like I had no example of non-convex function where I could prove that.
I see. I guess for the policy gradient example, we can do that.
Okay,
But,
thank you, yeah.
I guess practically speaking, I don't know if you do a little bit of a projection. I mean, the theory doesn't hold with projection, but I guess practically speaking, if you do careful projection, you might still empirically observe that. I'm not 100% sure.
And for the policy gradient thing, like this softmax policy gradient, they have like better convergence and like the endpoint convergence, right? More or less in the
So
function.
the way I parameterize the policy in my experiment is to use the softmax parameterization.
But for the softmax, like these recent paper by Chava and Jin Cheng, so they have like softmax policy gradient had like 1/t convergence rate.
So not exactly. So what they assume is that they have a perfect gradient estimate. So they do not consider the sample complexity they have for the gradient estimation. That
Yeah, but then like they also have like next paper that published about the bandits. In bandits, they can do with like stochastic.
banded, yes.
Yeah. So do like does the result the result that you have in your paper, that it extend to bandit and get better results? Or-
Yeah, if you have strong convexity in that case, then I can get 1/t convergence. Depends on, so basically for general policy gradient, the loss function is not even convex, right? But if
So
you
bandits also is not convex.
banded, yeah, that I'm not sure.
So I think you need to show some kind of gradient dominance, like PL kind of condition.
I see.
And yeah, so this, I don't know about like full policy gradient, but yeah.
So I like to make just comment that this is a framework. It falls in the framework of multi-component Markov chains. When components are adapted at some in different time scales, as you mentioned at some point. And there is a series of there were a series of papers. One of them was by Divavarasha, from MIT.
Deborah Shaw, yes.
Yeah, and he did several papers, and there is Alexander Proutier from KTH from Sweden, and so on. There was activity in the communication networks on that type of stuff. About 10 years ago, several papers. Yes, you may check this. Yes, okay.
Yeah.
But I think mostly when you have the different time scales, you have two component Markov chain. One is adapted in different time scale than the other one. So as you said, the first component is is adapted much faster, and the second is almost the same. And you have almost convergence to the station distribution here. Then you divide that, and so this type of scheme was adapted in Russia.
Yeah, so the multi-scale Markov chain, it's somewhat related, but I would say the actual setting is a little bit different.
Yeah. That's what you mentioned. Yeah, but if you do it one by one at the same time scale, I don't know.
Yeah, so there essentially, if you do the batched updates, it's more close to the multi-scale. Yeah.
So yeah, thank you. It would be worth to look at the paper by Divavrat. Have you seen these papers?
Yes, I've seen
there's
at least
several
some
of
of
them.
his papers.
Yeah. Okay.
Thank you.